Okay, today we'll be talking about how to solve quantitative problems with a momentum chart. Momentum charts are our diagram for this unit. Just like our LOL diagrams during our energy unit, we have momentum charts or IFF charts to help us keep track of the total momenta in a system and how it changes if an impulse happens. In this unit, impulse is the thing that changes the momentum in a system. Similarly, the analog last unit was how working was the thing that changed the total energy in a system before and after a change. Now, the thing here is that both require a net external force in order to take place, and it's even got a similar looking equation to working. If you swap out the t for an x, you find that you have our working equation. Also remember that momentum for any object is given by the object's mass times its velocity. And don't forget that signs matter. So in this momentum chart here, you'll see that you have a place for positive velocity as well as negative velocity. Likewise, in our impulse chart, you see here that there's a place for forces directed in the positive direction and then forces in the negative direction. In the previous unit, energy, we only cared about the heights of our energy columns. So now in momentum, since momentum can be positive and negative based on direction, we have to have kind of a bar graph in the bottom too to account for that the negative momentum. So there are two types of problems you'll see this unit, and the good news is that when you've seen a few of these, you've pretty much seen a lot of them. It's all a matter of turning the word problem into a picture in your mind, and then turning that picture into this diagram, which will then tell you how to do the math. In this unit, there are two possible problems you can encounter, and they don't really get much easier or harder than this. This is just what it is. The first possibility is a situation where you have no impulse acting on our system. So here, our impulse is crossed out, and we have the total momentum initially is equal to the total momentum in the final case. So for our class, this typically means that there are two objects that each have momenta at one point or another during the problem. Here in this diagram, even if the font is small, I can tell just by looking that in the beginning, before the collision, one object has a great amount of momentum on the left here and is traveling in the positive direction because its rectangle is in the positive area. Now, we also have another object moving, and this object I can tell is not as massive because its base is kind of skinnier, but this object is traveling in the negative direction with that negative 1 meter per second there, and you can tell because its momentum rectangle is in the negative area of the graph. Okay, so here we see that no impulse happens, so this part of the graph is blank. And then after the collision, it looks as though they both have the same velocity. So see how the heights of those rectangles are the same? If we have so much area in the beginning, you might think, well, how come the rectangle shrank? How'd that happen if there is no impulse? Well, it all has to do with the fact that since the object traveling in the negative direction has negative momentum, then what that means is that we have to sum these two up. And when you add a positive number to a negative number, you'll get something smaller for sure. And that's why we have smaller looking rectangles here. But in fact, this really is the same amount of momentum. So now for our class in high school physics, you'll pretty much see this possibility when you have two objects and each have momenta. So here we'll start off with two rectangles and could end with two rectangles. Now, in the second possibility, we have an impulse due to an external force. So this term does not go away. Notice that for our class, we will typically see only one object with momentum in this case, so we only see one rectangle in the before and one rectangle in the after chart. So however, we will have an impulse rectangle in the middle here. Notice that even without reading the problem, we can tell that some object is traveling in the negative direction because the rectangle here is in the negative region of our momentum chart. Now, as the problem progresses, I can tell that there's a positive impulse because there's a force directed in the positive direction up here that's going to change the momentum of this object in the beginning. Now, that impulse is so large that not only does this momentum become zero, but it even goes past zero to the positives. Okay, so that's one way you want to think about how impulse will change the momentum in terms of these graphs. Now, just between you and me, a really easy way to tell if a problem is an impulse problem or possibility 2 is if I start mentioning things like force in newtons or seconds in time. Then you can pretty much tell you're going to use the impulse equation because I'm telling you this stuff for impulse, but I'm asking you to find either force or the time. Another way to tell if there's an impulse problem is that usually in high school physics, at least in my class, you'll only have one object for these types of problems. Okay, so note you'll start with one object with certain velocity to have one momentum rectangle, an impulse happens, and then you have the final momentum. In this tutorial, you'll see that I'll do one example of each. Okay, so let's do a problem of the first possibility where there are two objects with momentum and no impulse due to an external force. So in this problem, one 3 kilogram lab cart moving to the right with a velocity of 4 meters per second crashes into a 1 kilogram lab cart that it's initially at rest. So I'm going to jot down their masses here. This one has a mass of 3 kilograms, and this one has a mass of 1 kilogram. So the problem continues and says, after the collision, the magnets on the lab carts cause them to stick together as they move down the track. Determine their velocity. All right, so I'm going to first start out by diagramming the momentum in the system before the collision. I have a cart that has a mass of 3 kilograms, so I'm going to go here 3 kilograms, so I'll go 3 blocks wide, and then I'm going to go 4 blocks tall. So here in this problem, we're fortunate enough to have numbers that are nice and allow us to use just 1 block for each unit. So here I've got 3 kilograms, and you want to make sure that you label your masses and velocities. So if I'm grading and you're not a great drawer, I'm able to see what you're thinking. And I'm going to label the height here of 4 meters per second, and that has to do with the left cart. So this is the momentum of the left cart. And I'm going to just jot down 12 kgs times meters per second for the left cart. Now, for the right cart, what we see here is that we've got a 1 kilogram mass, and it's not moving. So it really actually has no momentum. Now, I'm still going to represent it here by squiggling in this 1 kilogram for that cart, but I'm going to build it with no height because it's not moving. Things with motion, or things with velocity rather, are the only ones that get rectangles. Okay, now this, we said, is a no impulse problem. The problem does not make mention of any newtons for force or seconds for time, and we can't identify an external force, so that's not in play. And we're told at the end that they stick together. Now, there are a few ways you could do this. You could either keep the blocks separate, but when they stick together, and they will sometimes in these problems, I like to track them as one object. So here, I've got a base of not 3, not 1, but since they're stuck together, they're moving along as one object. So I'm going to jot down a rectangle with a base of 4 kilograms. Now, they're moving to the right, so I know to build my rectangle upwards. So the question is what is this velocity here that is the height of this rectangle? Okay. Now, I drew it a certain height because I'm making the screencast and I know what the answer is, but here's how we want to walk through this. Okay. So here initially, we have 12 units of momentum, 12 kilograms times meters per second. There is no change. Therefore, what we must have at the end is also 12. Okay, so we're just going to make a note of this here on the side, that what we want is a rectangle with an area of 12 kilograms times meters per second and base of 4, and we want to know how tall that rectangle is. So let's write this in terms of areas. So here, our area is just base times height, and we know that the area is momentum is equal to mass times velocity. So then we've got 12 kilograms times meters per second is equal to a base of 4 kilograms, and velocity is v. Okay, so just dividing that 4 from both sides, we've got velocity is equal to just 3 meters per second. Okay, so that's how you do a momentum chart problem where there's no impulse. So one thing I really like about these charts is that if you know how to draw rectangles, if you know what area is, if you know how to, add numbers like I did here at the bottom, the math work is really just what I have here in blue on the side. All I did was divide by 4 at the end of the day. So these do a really nice job of organizing what's going on in the problem. All right, so for our last slide today, what we're going to do is do a second example this time. We were going to do an impulse problem. So here we've got one object's momentum is changed by an impulse due to an external force. So here's what we've got going on. A 4-kilogram bowling ball has a collision with the ground when it's dropped. Right before it hit the ground, it had a speed of 2 meters per second. It bounces back up with a speed of 2 meters per second. Determine the net force on the bowling ball if it were in contact with the ground for 0.5 seconds. Okay, so let's start off by diagramming what the problem gives us. All right, so our system is just the bowling ball. So since it has a mass of 4 kilograms and is traveling downwards, what I'm going to do first is I'm going to establish this base of 4 kilograms. And this base is going to be labeled as such, 4 kilograms. Now here, I need to write that 4 kilograms up because I know that our ball is traveling downwards in the beginning. So I know that it's not going to get in the way, and my rectangle is going to be here because it's initially traveling negative 2 meters per second. Okay, so let's move on and find our momentum. Here it's negative 8 kilograms times meters per second for units. So just keep in mind what we want to figure out is the height of the rectangle that will be here, our impulse rectangle. All right, so before we do that, let's continue diagramming what we know. In the final case, we know that the ball has hit the ground and it's now moving with a velocity of 2 meters per second in the upwards direction. So here, I'm going to draw a line to represent the mass, right? Because mass is the axis there. And I'm going to build upwards by 2 squares. If I just say that 2 is that tall. And we've got 2 labels. So I've got my 2 meters per second, and I've got 4 kilograms here, which makes a momentum of 8 kilograms times meters per second. Okay, so here is where we're going to, again, have to stop and think just for a second and think, all right, I know I have negative 8 kilograms times meters per second of momentum to start, and I know I have positive 8 kilograms times meters per second of momentum to end with. So what kind of impulse had to have happened in order for this change to take place? Now, in order to figure that out, I suggest you just write out this as an equation above, kind of like what we did before. So before, we know we had 8, and I'm going to write down the units, plus something gives us positive 8. So this is an equation that I hope we can all solve here. Just -8 plus something is equal to +8. I'm going to work this out somewhere where I have space, so I'll just go up here. -8 plus x is equal to 8. I can add 8 to both sides, and I know now that that missing number has to be 16. So in other words, in terms of momentum and impulse, we know that the rectangle in the middle has to be +16. So I'm going to not draw this to scale here. So be careful. Every box does not have to be 1, and every box is not going to be 1 because not every problem is written with such nice numbers. But whatever that is, we know that the impulse has to be 16 newtons times seconds. And again, if you saw the last video, I talked about how the units of momentum, kilograms times meters per second, is the same as that newtons times second here. Okay, so now what we're going to do is take note of the fact the problem did tell us that the time is 0.5 seconds. So I'm going to place that on the time axis here. And all we have to do is figure out, okay, what is this force equal to? How tall is this rectangle? I'm going to do that work on the side, and this step looks just like the one we ended with the last problem. So area is equal to base times height. And we know that for impulse, which, does not have a symbol right now, impulse is equal to the base of that graph, so it's the change in time, times the height, which is the force. Okay, so I know that the impulse is 16 newtons times seconds. The time is 0.5 seconds times the force. In order to get the force by itself, I'm going to divide 0.5 seconds from both sides. We see that the seconds go away, and I'm left with a number that is in newtons. So here my external force is equal to 32 newtons. And that's what we got. So there's an example for a problem with impulse. All right, so I hope this helped. For my class, you probably will not see any problems much harder than this for our quizzes, tests, all that. Pretty much doesn't get much harder than this. The only thing you want to keep track of is the fact that sometimes our numbers are not going to be as nice as the ones in this video. So you want to make sure that you're labeling the numbers appropriately so I can see if I'm grading. Okay, so anyways, that's it for examples. Hopefully the screencast helped you out a little bit during your momentum problems, and I'll see you in class.